Today's class is in some part to make sure you're in the right place, make sure you actually want to take this class, because it's a very good time to decide not to take the class if you don't want to take the class. It would be terrible if you think you're taking one class and you end up with another one. So that's the biggest thing that I want to get out of the way. But we also are going to try to cover a little bit of the material. And in some sense, today's lecture is actually really important because we are going to set the context for everything that we do in this course. The course is essentially a tour of the solar system, but it's also much, much more than that. Now, there's a lab that goes along with it, too. I don't know, probably most of you signed up for the lab as well. The lab requires you to download a software set, which is essentially an online observatory. It's pretty cool because you can go and explore the sky throughout time. You can go back and look at the sky the year you were born. You can go look at it the year Plato was born if you want. And you can look into the future as well. And there's different exercises and so forth. So all of that content is available through Moodle, and actually everything in this course is going to be available through Moodle. So what you're going to want to do is, if you haven't already checked out Moodle, that's where pretty much everything's happening. That's where you're going to submit all of your assignments and everything like that. Now, what I'm going to do right now is pass around this attendance sheet. And I know this is kind of a drag that we take attendance in this course, but the fact of the matter is that it's really important that you come to this class, because what we're going to do in this lecture series is we're going to talk about why what you're reading in the textbook matters, because it's not entirely clear from the textbook why it matters. Most people think about the stars in our modern age, and it's something of a casual curiosity. But they've been really, really important to humans for thousands and thousands, if not millions of years. The stars were the way that we learned how to live because we told our stories. We didn't have Netflix back then. So what we're going to do in this lecture is I'm going to stand here and I'm going to tell you guys stories, and you're going to sit there and hopefully soak it up. And you're going to ask me questions, and you're going to stop me when you have ideas, and we're going to discuss them. That's how this course is going to work. So if you don't like classes where a guy stands at the front of the room and talks to you for an hour, drop the course. Otherwise, it's going to be a blast. It was really fun last year. I was actually really excited to see you guys all chatting amongst yourself this morning. When I taught this course last fall, people were coming off the pandemic, and it seemed like folks were a little more closed off to one another. So this is wonderful that you guys are hanging out. I do want to try to maybe do something. I tried this with the second semester course last year, and I don't live near campus or anything, so I don't just sit around in my office here. This is just a part-time job for me. I do a bunch of other stuff. So look, if you guys want to come early on Thursdays, I'll brew a pot of coffee. We can hang out, we can talk about the universe, we can talk about anything in the world if you want to. You can hang out with your friends, whatever. I like to just have essentially a little open auditorium there at 8 a.m. every Thursday. So I'll open the door at 8 a.m. Thursdays. I hope you guys will want to come hang out. At least just come, meet your classmates, get a chance to socialize. If you want to talk to me, we can do that then too. Cool? All right, so we'll call that the coffee hour, even though it's actually a half hour. Hold on, I lost my pen. All right, attendance. Let's start that zipping around while we're here. So if you could just pass this down the back and forth like a S through the rows. I know you're in a row by yourself, but send it down there next. All right, cool. So most of you guys are probably not science majors, right? No, sir. Yeah. So that's wonderful, because this might be your only chance to actually think about what science is in some more depth than you might get from, say, Google News or wherever else you hear about science, or Bill Nye or Neil deGrasse Tyson, right? We're going to think about science a little bit differently than you're probably used to, because I think science is a lot more than it's cracked up to be. And I think it's much more of a creative discipline. And so this class is really going to be about how we come to know what we think we know and the pitfalls of believing in what we think we know. Because the most interesting thing about science is that it's always on the move, right? And so we can get locked into this perception that we know how everything works. But there's almost no better topic in the whole world than astronomy and astrophysics to realize how much what we know is changing every single day, especially planetary sciences. You know, we thought all of our body of knowledge about our solar system and how planets were formed and how they mature and age, it was based entirely on our solar system forever until about 10 years ago when we were finally able to start looking at other planets. And what we learned when we start looking at those other planets is that when we look at those other solar systems, is they're very, very dissimilar from our solar system. Most of those solar systems have the same type of planet. That same type of planet that most of those solar systems have is not found in our solar system. So we're kind of an oddball, and a lot of our theories have been based on assuming that all solar systems would be like ours. They're not. And so this makes for a really, really dynamic knowledge sphere with regards to astronomy. Everything is changing really fast right now. A lot of the things we're going to be talking about are completely theoretical. Now, that doesn't mean they're worthless. It just means that's our best idea of what's happening right now. So, again, we're going to be talking about how we come to know what we think we know, and how reliable is that knowledge, and how will it change in the future. And that's really important. All right. So that's kind of what I'm going to crack open today in this class. I want to tell you a tiny bit about who I am, because it might be nice to know who this guy is talking to you right now. Like I said, what's astronomy? What's science? Talk a little bit about physical laws. So there's a little bit of math in this class. Don't worry, don't panic. It's not that bad. There's each week you're going to have a textbook reading assignment. There's a short online quiz you take for that, so that we don't have to waste time with it here. And it's really simple, right? You can take as many tries as you want to finish those quizzes. There's no time limit. Don't get stressed out about it. If you have any problem with anything, send me an email. I can meet with you on Zoom. We can meet on Thursday mornings. Whatever you want. It's not that big of a deal, and the textbook's going to walk you through each one of those calculations. And in general, we're going to try very hard not to get lost in the math, because the math is really useful in a technological sense, right? If anybody here decides to become an engineer or anything in that domain, you're going to find math extremely useful. But when it comes to understanding how things work, it's a very qualitative pursuit. And so I think that concept has been lost a little bit in science. And we're gonna avoid that as much as possible. But we do have to talk about a few things, right? Because in some sense, math is how we catalog our observations. And that's important in terms of coming together, putting together a concrete story of what's going on. All right, so we'll talk about numbers a little bit and scale, because everything we're talking about is extraordinarily large. It's incomprehensibly large. So we'll try to put some tags on that so you can handle it. And then, if there's time at the end, I want to take you on a brief tour of the universe. And of course, like I said at the beginning, what we're going to do in this course is we're going to go in with this absolute luxury of depth into each piece of the solar system, right? We're going to start at the inner planets. We're going to work our way outward. And by the end, we're going to have covered the entire solar system. We'll have looked at all of the different types of planets. We'll look at all the moons, the asteroids, the comets, everything like that. If you want more, sign up for the course next semester, because we're going to figure out how stars work. It's an astrophysics course, and we're going to talk about cosmology a bit more in that course as well. So the universe in general, which in some sense, you know, that's got probably more of the popular science topics that everybody's interested in, the black holes and the Big Bang and all of these things. And so we'll touch on some of that stuff, but most of that's next semester. Is everybody in the right place, more or less? You didn't mean to come to like a chemistry class or something at least? All right.
Is Nora actually added her name to the roster?
Yeah, if you're not on there, make sure you're registered, though. Yeah, if you don't see your name, pen it in.
What was the second page?
There's,
Yeah, I think.
oh, there are 2 pages there.
You wrote your name at the bottom of the first page. Yeah, I checked it.
Thank you. I need a little help.
All right, I think I've told you a bit what to expect from this course already. Oops. All right, this is important. Kind of boring, but it's important that you understand. How are you going to be graded in this course, right? So in some sense, college is supposed to be this wonderful place where you go and I teach you things about the world, and it's fantastic. But unfortunately, I have this other job where I have to evaluate you. And I'd rather not have that job, to be honest with you. I'd rather just come here and talk about the universe. That would be much more fun for me. But I do have to evaluate you. And so I inherited this course from somebody else. It's essentially the exact same grading structure as it's been for years, as far as I know. And so let's go over that a little bit. Like I said, there's going to be this weekly quiz. It covers the textbook material. If you are taking the lab course, there's also a little quiz that goes along with the lab assignment. There's also going to be a video assignment every week. It's very easy and very short. Essentially, you're going to check out the watch list on Moodle. I put up, I'm adding to it, and the previous professor had added some different videos. But they're topics, they're usually like YouTube videos, short 5-10-minute YouTube videos that relate to something to expand it that we've been talking about in class. And what I want you to do is give a response. This week, it's easy. All you have to do is essentially introduce yourself to your classmates. And we use this platform called Flipgrid. Flipgrid's cool because it allows you to respond to other students' material, and so there will be the opportunity that you do that instead of a new response at some points during this course. All of that is building up to the fact that the majority of we don't have a final exam in this course, so everybody, that's a good reason to take this course, first of all. And there's going to be no exams. So if you hate exams, I hated exams. I think they're a little bit silly because you learn all this stuff and you forget it as soon as you leave. So instead of that, we're going to do a project, okay? There's actually 2 possible projects. One is required. This is your final project, and it's going to be a video presentation. You can work with somebody else if you want to. But you're going to go in depth and research some topic that we didn't get into enough detail as you might have liked in this course. So I'll publish all the details for that. They might actually be published, I'm not sure. But I'll put them up at the relevant points. But the weekly Flipgrid assignments that you're doing, the weekly video assignments, they will be, in a sense, getting you ready to do that final presentation. It's nothing to worry about. It's not a big deal. The point of this course is not to freak you out and to make you have a hard time. It's so that you can genuinely get some appreciation for what we're trying to do in astronomy and why we actually do it. Who cares? It doesn't seem to matter necessarily to most people. But it actually does matter a lot, and we'll try to hopefully impress that upon you by the end of the course. All right, so quizzes, weekly video, and the final project. Now, here's the kicker. Oh yeah, and attendance too. Look, the reason, like I said, we have to have an attendance grade because you need to be here at this course. It's the only thing that gives the textbook some relevance. It's the only thing that gives the material a context that makes sense. I could just give you guys a quiz every week, but that would be kind of stressful. So let's just sign this attendance sheet every week or every class and call it a day. All right? And that's not an insignificant portion of your grade, by the way. So it pays to come. And honestly, I don't really want to be lecturing to an empty room. So please be here. Final piece, which is pretty cool, is that you have the option, if for whatever reason you're whiffing on these quizzes, your grade's flagging for whatever reason, you can do an optional creativity project. It's worth a lot of points relatively, okay? That thing can be anything in the world that you want as long as you peg it in some way to astronomy, astrophysics, the stars, the cosmos, which is basically everything. So you need to do some sort of creative project. I've had students do paintings, murals, videos, time-lapse, sky photography, poetry, short stories, literally anything. And essentially, you're going to get as much extra credit as effort that you put into it. So it's very subjective, and if I think you put a lot of work into it, it could really save your grade. But your grade probably won't be that bad because it's not a hard class, okay? As long as you do the work, you're going to get an A in this class. That's how it works. All right? Questions about all this boring stuff? We can talk about the universe a little bit. Oh, one more thing. Let me introduce myself. So my name is Dr. DeLay. And my background's actually in atomic mechanics, right? So I actually was studying the elastic behavior of water during my PhD. And you might think that's kind of a strange person to be teaching you about astronomy, but actually water is one of the most important pieces of the puzzle, and we'll see that as we start to look at how planets are formed and how life develops and all of these things. Furthermore, everything in the world is made out of atoms, right? Everything we're going to be talking about, from the planets to the stars to you in this room, it's all made out of atoms. And more importantly, the way that we go about interrogating ideas and the way that we comprehend science is the same in almost any discipline. So don't get too hung up on that. So I'm not a professional astronomer. I do have a telescope. I like to look at the stars. I have a real passion for understanding what's going on out there. I mean, I think that's basically enough. I've also got a podcast too, which you'll probably be referencing a bunch with my wife. It's called the Demystify Sci Podcast. It's pretty cool. We call up different scientists and philosophers, and we essentially try to pick fights with them. It's very fun. And so we're very kind. We're not mean, right? But the fact of the matter is that there's something which I think that will reveal itself more and more as we go through this course, which is very frustrating to me as a scientist, which is that science is often presented as this monolithic understanding, right? Here's how things work. We know this is how things work. Shut up and listen to us. But that is very, very far from the truth of how things work. I can guarantee you that everything you're going to learn in this textbook today will be totally different from the students sitting in this room 100 years from now. That's how science works. It changes. It changes as we learn more about the universe, as we come up with better ways to integrate all of our knowledge. Okay? So anyways, that's what I do with my life, pretty much. We make short films. We do a lot of stuff. We're curating some museum exhibits in New York and Miami right now. But essentially, I concern myself with knowledge and how we get that knowledge and what we do with it. And it matters a lot to me because the future matters a lot to me. And if we don't understand our universe, then it's very difficult to orient ourselves towards a better future. And that's kind of what it's all about here. All right, enough on that. All right. Anybody recognize this? This lighting's kind of poor here. This is Crater Lake. You guys been there before? Cool. Yeah, so imagine yourself at Crater Lake before there were electric lights, before there were TVs, before there was Netflix. And imagine that this is all you had every single night was this set of images passing over your head. What would you make of it? What would be something that you would notice about it almost immediately? Say you'd been alive for more than a few days. What would you notice?
The Milky Way crack in the sky. That's what I would think.
Yep, that's a huge, so there's features, right, that are constant. And they appear every single night. That's what's crazy about it, right? There's something very regular about that. And the truth is that regularity is extremely comforting to all of us, right? We're going to find, actually, as we move through this course, it's going to be less and less of a strain for us to come here every morning and do this because it's going to become regular. The first time I have to come here and talk to you guys is very stressful for me. I'm like, am I going to be able to do this or whatever? Because it hasn't become regular yet. By the end of the semester, I'm going to just be like doing this in my sleep, essentially. Regularity is comforting. Now, the sky itself, these patterns that appeared were very comforting. And what started to happen over the course of civilization, we're going to get into this more and more, is that people began to take inventory of that predictable behavior. And the people that were able to make those predictions inherited some power in those civilizations, in those societies, right? If you can tell me exactly where the moon is going to appear in the sky the next night, or even better, if you can tell a crowd of people that the sun's, well, they didn't know this, but let's say an eclipse is going to happen tomorrow. That gives you a great deal of power, right? And power and organizing structures are really important for societies. Because at some point, look at this room right now. None of us are concerned with going and growing crops in the garden today, right? Somebody's doing that for us. That requires a stratification of society. That means that there has to be people who do that, and then that frees up the time for people like us to sit around and think about big ideas, which is pretty crazy if you think about it, because for the overwhelming majority of human society, let's say human existence, people were concerned with staying alive primarily, right? We were in small groups of people. We spent our days hunting. We spent our days foraging. Maybe there was some gardening, a little bit of primitive gardening, but that's how we spent our time. So I would submit to you that the ability to make these predictive announcements about the sky and the way that the year would progress from year to year was not only instrumental in the birth of agriculture and being able to plan harvests and plan your hunts and understand animal migrations, but it was really important in being able to start to organize the society around people. Oftentimes, the people who were able to make those predictions were the people who were the authority structures in those very primitive societies. So this is really important. And it's hard for us to imagine because today, we're so far from spending all of our attention at night on the skies. But at some point, not too long ago, that's what people did. This is what they had to tell stories by. And the stories that they concocted were not these silly, primitive, superstitious stories that you might think they are when you see them at first glance. They're very rich with meaning about how to live our lives. Okay? And that seems to be something which is increasingly receding from us in the modern world. It's very difficult to find information about how to live in the world. We have entertaining things, right? We have Netflix, like I said, or whatever you guys watch, TikTok and whatnot. It's very entertaining, but it's not entirely clear that it teaches us about how to behave in the world in a way that promotes our own success in the world. And the ancients were obsessed with that. They were obsessed with how to integrate themselves into the cosmic structure. And so one of the wonderful things about this course is that we're going to have time to think about how other people besides us thought about the sky. And we're going to look at some of the different mythologies that surrounded the different apparitions in the sky. What did people make of the moon before they realized it was a rock, right? And that was a long time before people realized it was a rock. What did people make of the earth? What did they make of the sky? They weren't idiots. That's really important. They weren't just these superstitious, silly people. They were rich with experience and understanding about how to hold a group of people together in a productive fashion so that we weren't all gutting one another and taking each other's crops and things like that. They understood that these things in a way that in some sense beat out the way that we understand it today. And I think that that's something that we're going to try to spend a lot of time making sense of. You know, well, so you might have noticed, to that point, you might have seen this before, right? We have these things in the sky, right? People call them constellations. And you might have, when you were a kid, someone might have said, that's the bull up there, right? And you might have looked at it as a 10-year-old or something and be like, what are they talking about? This looks nothing like a bull. What is going on here, right? That's because it's not important that it looks like a bull. What's important is that that's what the ancients used to tell the story of the bull, which we'll get into in great detail later, which was really important for teaching them the different patterns that they needed to survive in the world and teaching them how to have a coherent society. And so those stories actually are still the names that we use. In modern astronomy, we still orient our telescopes based on their separation and location within these constellation systems. These names still stick around. That's how important they are, actually. Cool. Yeah, you just pass it up here. Okay, but it's not always the same, right? So actually this bull one appears in a lot of different, appears in a lot of different cultures. But in some other cultures, you might say if you were in China, maybe you would see different feathered serpents and tigers, right? Instead of the twins of ancient Greece or the fish, the Pisces, right? You might see something slightly different, but the stories actually, or say we're in this is, I believe, an Aztec sky map, okay? You see these serpents and so forth, feathered birds as well. But the stories that they told were actually remarkably similar, and I think that's where things start to get extremely real. Because these people had no knowledge of one another. It's not the case where, look, the migrations happened tens of thousands of years ago in many cases. In some cases, hundreds of thousands of years ago, when you talk about the East, which was separated from the West. They still come up with remarkably similar stories about some of these. The story about Venus is almost identical between the people in ancient Mesoamerica, down in Mexico, and the people in Sumeria. Did they know each other? No. they came up with the same story. Why? Because there's something fundamental that happens in the human experience, which is recapitulated in the sky. And it's very easy to use the appearance and disappearance of Venus. Look, Venus, we'll get into this more later. Venus disappears. It shows up in the morning for about more than half a year. Then it disappears below the horizon for 8 days, and then it appears in the evening after that, right? So this story of descent into the underworld and wrestling with the unknown comes up in each one of these cultures, and they map it onto that apparition in the sky. This is extremely significant because it gets at something convergent about all of our human experiences. So there's more to this than it just being than astronomy just being this tool, right? And of course, it's an extremely important tool, like I said. If you're trying to plant your harvests, if you're trying to track the game that you're hunting, it's extremely important to be able to time when those things are happening, to know when in the year you are. Because the animals inherently know that, and they're going to migrate based on it. The fish are going to be in different places at different times in the year. And of course, anybody who's ever tried to grow anything, any of you guys ever tried to grow anything before? All right, it's hard, right? It's very, very hard. It's very easy to mess it up and have very bad tasting vegetables. Trust me, I had really bad garden this year. And because I left for about a month in the middle of the growing season and everything went terribly. So look, you can't mess this up. You have to be really in tune with the seasons. So there's something instrumental about it. Being able to clock everything is very, very important. And we'll look at how people have developed different clock systems using the sky over the last, 50,000 years or however long it's been since humans have really been concerned with this. It's very difficult to tell ancient history beyond a certain point. It's very difficult to tell what happened 500 years ago because the people who came out on top write the history books and you don't really know. You go back 1,000 years and it's even murkier. You're at some point listening to a game of telephone where people are telling the story of the person who told them the story, and you have very few archaeological relics at 10,000 years. The Earth, the northern hemisphere, let's say, was largely covered in ice for another 10,000 years before that. It's just a mess. So we don't really know when this all started, is the fact of the matter. But we have some ideas, and as far as we can tell, people have been very concerned with the sky for that entire time. So let's look at a couple of examples of that. So this is a piece of bone that was carved. This is found in the Near East. I'm not sure precisely where. But they actually are noting these star positions on the back of this. This turns out to be on the front side, it turns out to be a picture of what we would call Orion today. And this was, I believe this was over 10,000 years ago when people were doing this. They were making charts of the sky. "30,000 BC. Okay, that was a long time ago. That's before the Ice Age. This is a very famous cave painting. If you ever heard of cave paintings before, this is probably the one. This was, let me see if I can get the name up here. Yeah, this is the Lascaux. This is a French word, cave. This is between 30,000 and 10,000 BC. Again, huge range of dates. It's very difficult to tell how old something was. Actually, if you want to figure out how old something is, there's only really two ways to do that. One is you look at where it is with respect to other things. So you make some sort of relative date, right? Things pile up in the muck over the years. This is very imprecise. You can also possibly use some high-tech means of doing it, like we call radiocarbon dating. Or we say maybe with rocks, you can just look at radiometric dating. Now, those seem like they'd be wonderfully precise and so forth, but the fact of the matter is that you need a carbon source to be able to pull that off, and you need a carbon source that actually was fresh at the time that that artifact was found. And so that's why we get these outrageously large spans of dates, because people don't actually know, for the most part, when these things happen. They can kind of ballpark it, but it's very difficult. All right. Stratigraphy, too, is a mess also. Sometimes there's huge pieces. Have you guys ever gone down to like a river or creek and you can see the different layers of sediment, right? Has anybody been to the Grand Canyon before? Yeah, pretty crazy. Now, the Grand Canyon is wonderful because they have all of these layers, but what's really astonishing about going to the Grand Canyon is there's one point down near the bottom where there's 1 billion years of time that's just absolutely missing from the record, just gone. They can find it at other places in the world, but it's not there at the Grand Canyon. So what happened, right? What scoured 1 billion years of the stratigraphic record from the Grand Canyon? No one knows. But it happens, okay? So stratigraphy is not extremely precise. It's at best going to give us this sense of before and after. This happened before this and after this. That's about it. All right, so we have to be really careful with our dating. And actually, this is as good a time as ever to point this out. But, you know, your textbook oftentimes will say something like, the Earth was formed 4.5-ish billion years ago. Why do they think that? Anybody? Yeah.
Can you check the age of like rocks and layers and stuff?
They actually do a radiometric dating of it, okay? But if you gotta ask yourself, what are they dating? Well, what they're saying is that the oldest rocks we can find are radiographically dated to it's not quite 4.5, but let's say 4 to 4.5 billion years ago. Well, what are they actually looking at? So there's an assumption there that the oldest rocks that they found are the oldest rocks, which, okay, let's give them that. There's also the assumption that how this method tells us the date. And here's the thing. Radiographic analysis works like this. When a fresh piece of radioactive isotope, they use lots of different radioactive isotopes. So a lot of atoms are unstable. When they're first generated, they have a lot more energy in them, they're contorting, they have more folds in their surface and so forth, and they decay down to lighter elements. They break apart. And as this happens, you can measure how long that takes. It's very predictable. And so what they look at is they look at how the ratio of these big unbroken elements to their daughter elements inside of these rocks. This is actually a really reliable way of dating something. The problem is it assumes several things. It assumes that the time when this rock formed was the first time that it formed. This is actually the biggest, most difficult assumption of the entire method. So all that these radiographic analyses can tell you is the last time that this rock melted, okay? So these rocks that we have that we say, hey, the solar system, the Earth is 4.5 billion years old. Well, that's the last time the thing melted, the whole face of the Earth melted. That's all we can say about it. And so we have to be really careful with these dating things because, again, the more we learn, the more these stories are going to change. Case in point, something like 200 years ago, most geologists thought that the Earth was about 6,000 years old. About 100 years ago, most astronomers, all astronomers, believed that the entire universe was inside of the Milky Way galaxy. How about that? So things change really fast. Our understanding changes really, really fast. Now we know that there's trillions of galaxies, just like our own. Okay. So I'm going to be touching on this. I'm going to use this book as a companion, which I think is really good, just to try to frame some things for you because, you know, we're here in North America, and people have been in North America for a long time, and they've been telling some stories about the sky. So I think I'll just read you a little passage of this today just to give you a preview of, for example, how the Navajo people looked at the sun, moon, and time, because it's very different than the way that we do, and I think that's going to become important. And we'll have more time for this as we go forward. Let me pull this out for you. All right. We're trying to comprehend the meaning of the sky to people before it was this very orderly system of rocks crashing into each other and burning in the sky. The holy ones then realized that the universe needed light. They also realized that there was no order, direction, or sense of time or measurement initially. Okay, it was chaos. The holy ones again collaborated to address these needs. First man and first woman brought the energy of the sun, moon, and a crystal star from the first world, In the second world, Coyote, first boy, and first girl were created, and together they brought the knowledge of heat and light from the clear crystal to the fourth world, that's ours, all of which was eventually used to produce the sun. The holy ones decided that the sun, considered to have male characteristics, would provide order to the days and seasons. The seasons are recognized by the location of the sunrise. Referred to as the day traveler, the sun is used to determine time in a general sense, as well as to determine the cardinal directions. The equinoxes and solstices are considered sacred times of the year, the end of the sun's journey marking the passage of time and the seasons. Blessings Way ceremonies are held to ensure that the actions of the people and the earth are in harmony. At these times, it is said that for thousands of years, the sun, moon, planets, air, water, and electrical forces have aligned themselves at these times, a universal alignment where energy is shared. So look, if you are thrown into the woods all by yourself, let's say it's a very bewildering experience, but very quickly you're going to start making up systems in order to handle your daily needs, right? Your ways of getting what you need, building shelter, finding food. Let's say I throw 2 or 3 of you in the woods. Now you got a new problem, right? Because let's say you're not friends. Now you have a much bigger problem than just finding food because you have to get along with these people. You have to organize yourselves. And this turns out to be the fundamental question of society is how do we get along with each other? And the stars turned out to have been imagined, of course, in this Navajo tradition, the sky, they give it this male characteristic, and we'll come back to that. They give the sun this male characteristic of order, which is really interesting that they ascribe the masculine to order. And we can talk about that a bit later. Why do they do that?
Like their social structure?
And why would they prepare this social structure? Because it's useful. They found it useful for some reason, right? Look, men are extremely dangerous, first of all. Without society, men are extremely dangerous. They have a strength advantage on women. They can be very predatory. They can be very aggressive with one another. So if you don't have a social structure to put those men in order, right? In other words, to rank them by something approximating their ability to act as in those leadership positions, their competence. If you don't value that and treat it with cosmic dignity that it deserves, you can end up with a really degenerate society where you have a bunch of really dangerous people who are doing all sorts of shenanigans, okay? So this was extremely important, and the fact that they peg it to the sky, something beyond themselves, is also not insignificant. So if we go back, now these stories, right, that the Navajo are telling have been around for tens of thousands of years, as far as we can tell. But the first real evidence that we get of people inventorying these things don't come till much later. We have those star catalogs and so forth, but the idea that they would instrumentalize it, we don't see until we start seeing these huge monolithic structures, like this one. Has anybody been to Stonehenge before? Huh? I went there when I was a kid. It's pretty magnificent. So I recommend that you go if you have a chance. But, when people first started reinvestigating Stonehenge, they thought, oh, this is cool. These people built these monuments to their gods and so forth. Well, very quickly, they realized that on the summer solstice, and on the other solstices for that matter, that the sun would rise and set in a particular location between these columns, right? The thing was a calendar. Yes? Where is Stonehenge? Yeah, it's in England. Yeah. It's a train ride away from London if you're ever out there, if you ever find the chance to get out there. It's well worth the travel. And there's a lot of other really cool stuff, a lot of cool history there too in general. Oh, I could say so much about that, but I'm not going to right now. So the first calendars, right, were essentially these stone circles. Stonehenge isn't alone. We'll look at a couple of other ones that are potentially even older. One of the first ones that we are aware of is actually before dynastic Egypt in Africa. And there's maybe some that are even older in South Africa. But again, it's very difficult to say when somebody put a rock somewhere, right? The rock is much older, of course, than the people who put it there. And it's very, very difficult to make these claims. At any rate, people started setting up these calendars, right? Does anybody know what the solstice is?
Like specifically the summer solstice or the solstices in general?
Yeah, let's talk about the summer solstice.
The summer solstice is the day that you can see the sun from where you are on the earth the longest.
Yes, yeah, exactly. It's the longest day of the year. Now, does anybody have a sense of why that is? And we'll go over this more and more. But it's okay, cool. Somebody we haven't heard from, yeah.
Because of rotation of our planet, we are slowly on an axis tilting from side to side. So during the summer solstice, we're tilted more towards the sun than usually when we are with the winter solstice.
Yeah, so it's actually, you're right, and it's a little bit more, it's a little simpler actually than that. So the tilt of the Earth is not changing, which is interesting. So that's maybe one conception. So the Earth is tilted quite a bit at the side, right? But as it makes its nice orbit around the sun every year, it finds itself, and you can see in this picture here, it finds that the northern hemisphere at some point is pointed more towards the sun, and at some point in the winter it's pointed away from the sun. That's why it's the opposite experience for people in the southern hemisphere, right? I talked to, it's very bewildering to have friends who live in the other hemisphere down below, because they're having the opposite experience of you at all times, which is very strange. I have a few friends in Australia. It's very bewildering. So they're having summer when you're having winter and vice versa. Okay, now this is really important. So this, as a result of this, it means you have more light in the sky in the summer, and at some point you have the most light. And that is essentially where you make the starting point for your clock, right? That's when you know that the year has come full circle. And you can, of course, do the shortest day in the winter. And you can come up with this very regular clock. Now, what comes next? What comes next is you need to subdivide that thing, right? Because it's not entirely useful. You might say, by the way, this is that even more ancient stone circle in Egypt. This is before the ancient Egyptians as you know it, right? These are pre-Egyptian people. But people had to divide it, right? And what's a nice divider? Well, the moon, actually. So does anybody know how long does the moon take to go around us? Yeah, I see some people like 30. It's almost 30. It's like 29 and a half days, okay? This turns out to be a wicked problem, actually, for the ancient astronomers because they really wanted it to fit neatly into that solar calendar, right? They really wanted to say, there's 12 moon cycles every year, right? That would be wonderful if it was the case. That would be super useful, but it is not the case. And so what we find is that all throughout history, people are trying on different ways of reconciling how the moon calendar fits into the sun calendar. And so this is one attempt. This is from ancient Scotland, actually, where they're actually marking the phases of the moon that you should expect so that they can tack on that extra bit of time each year. So they know, okay, we have a little bit more of a moon cycle this year than we did last year because it's not quite 12, right? And that's really, really troubling. Now, I have a sense, I'm almost certain that people were concerned, they clocked themselves to the moon, maybe even before they clocked themselves to the sun. Does anybody have any idea why I think that?
Because wasn't the sun super helpful in like agricultural calendars?
That's one reason, for sure. What else is interesting about the 30 days of the moon? Yeah.
With the sun coming up, it like doesn't change in any way, but the moon changes. So it could show like a difference, like time passing.
It's definitely a smaller increment, but there's something really special about the 30-day length of the moon's cycle. Ladies? Yeah, go ahead. The period. This is actually pretty crazy if you think about it. It seems like something a little bit more than a coincidence, actually, but the female menstrual cycle is actually also 29 and a half days, okay? So I think for most of evolutionary history, women were clocking their menstrual cycles to the moon. Now, this is really, really important because it allows people to recognize, look, humans, unlike most animals, the females are actually very, how should we say, their ovulation is actually rather secretive. It's not entirely clear when a woman is ovulating. Okay, this is actually very important and strange in the animal kingdom. In many, like say chimps, right? When the female chimps go into heat, it's very obvious, right? They have changes in their bodies that are quite obvious. All the males know that it's time to do their business. Okay, humans don't do this, which is interesting because it puts women in this very selective role in society. Women get to choose when they're going to have a baby. And obviously in our modern age, this is a much more safe choice than ever before. But women were able to actually clock themselves, and there was some understanding, I think, that was linked to this. So anyways, the moon cycle, I think, was something that was really important even before agriculture. Like you said, agriculture is probably the first time that people really cared about the sun, because that involves when to plant, when to harvest, when to avoid the monsoons, all of these things. But I think that the moon cycling was extremely important. So, people actually labored and labored and labored over how to fit the moon into the sun cycles for almost up till modern times, okay? So we came up, and we'll do a little section at some point in one of these talks. We'll talk about how the calendars were developed over the years. But it was very difficult, Actually, the one that they came up with that they used through the Middle Ages, as far as I can remember, I don't have the date off the top of my head, but it was wrong, right? The church had set something up, the Catholic Church, and it didn't work out because it wasn't clocked perfectly, and they needed to add these leap years, right? Every once in a while, you got to just deal with that extra piece of time. Otherwise, what happens? Well, they were finding that Christmas was moving into springtime, and this didn't work out, right? And there's lots of reasons why they needed Christmas to happen at the winter solstice, and we can get into that as we go forward. Anyways, so the moon, it mattered. All right, so this is another attempt by some ancient people. This is in Germany, not too long ago. I mean, 4,000 years ago. Also, this is a means, and I can't explain it to you exactly, but they're trying to sync up, say, when the full moon will be with respect to the solar year. All right, so at some points, fairly recently, but again, thousands of years ago, but still, let's say at the birth of civilization, something really interesting happened. And one of our best resources for that is ancient Sumeria, and in particular Babylon. Now, that's not to say that there wasn't contending astronomy appearing in ancient China and in ancient India. There certainly appears to have been, but in all honesty, those are very impenetrable archaeological situations. The Sumerian script is well understood. We can read their writing. We can read their star catalogs. No one has deciphered the ancient Indus script to this day, all right? It's also very politically difficult for people to work in that system right now for whatever reason. What the heck, I'll just explain it. So what happened was India was under colonial control until, really right, World War II, essentially, sometime mid-20th century. So the British archaeologists were the ones who showed up and really did all of the initial work on the Indus Valley civilization, which was contemporaneous with the Sumerians, right? We're talking about 3000 BC, maybe 4, maybe 5, 6, 7, but several thousand years ago, one of the first civilizations. Anyways, the British archaeologists show up, and of course they start immediately concocting stories about how these people are essentially descendants of their Indo-European tradition and basically received all of their wisdom and knowledge from the Europeans. Now, the Indians didn't like that very much, which is understandable. And so after the British colonials left, they kind of walled off their archaeology from the West. And so it's very difficult to get a cohesive story going right there. So we're going to focus on the Sumerians because we can read their writing, because the archaeology is open to us. And let's take a look at them, because I think what happened in Sumeria was in some sense archetypical, generalizable as what happened in the rest of civilization. So one of the first things we find is that the Babylonians began to make these very intricate catalogs of where the stars were in the sky. They also created a map for it, which they quantized, which is really fascinating. So the Babylonians, unlike us, they didn't count in groups of 10. They counted in groups of 6 and 60, right? And this is somewhat perplexing, right? Because it makes sense to count in 10. Like, we all have 10 fingers, right? You can do this, and you can count. There's some debate as to how they came up with this. The best one I've heard is, I guess, because you have these 3 digits on each one of your hands, and maybe you can count in groups of 6 that way, something like this. At any rate, it wasn't insignificant, because if you notice, we still have 60 minutes in an hour, right? We still have 60 seconds in a minute. The way that we divide it up by 6 is directly related back to these Sumerians, 5,000-6,000 years ago when they came up with this system. We still use it today because they were the first ones to divvy up the sky into these minutes. And we'll talk about later when we get to the modern astronomy a bit next week. We'll talk about how we still use that. We still talk about minutes, and when we are trying to locate where a star is, we divide the sky up into a circle just the same as they did. Okay, so they established this for us. Another thing that was really interesting that appeared in Sumeria was that you had the first real evidence of a class of people who were the astronomers. And this is very bizarre, and I don't think the depth of this is very bizarre in that I don't think that we've seen anything like this since. The Sumerians appeared to have an actual ethnic group of people that lived in one part of the city. I believe, it would be on the west coast of the Persian Gulf there, near Babylon. These people were called the Chaldeans. Now, the Chaldeans appear to have been the people who were the record keepers, the astronomers, the people who interpreted the sky. They weren't the ruling class. In fact, they weren't really even treated that well, which is quite fascinating. So you see this stratification where you have a group of people that's actually able to separate. There's some division of labor in this society. And you actually have people that are able to take their entire professional time. Somebody's feeding them, right? This is a very unique moment in history. These people are not working in the ordinary sense. They're like us. They're sitting around thinking for a living. That's very bizarre and very new. And astronomy is right at the heart of that situation. You might think, and of course this allowed there to be an actual state with a bureaucracy and so forth. Now, there's people who just sit around groan, it's very easy to groan about the bureaucracy of our state, right? And it's very easy to talk about how our state is such a, oppressive system and all of these things. Trust me, it absolutely is in many ways. But the alternative is also extraordinarily unimaginable. Think about it this way. There are places on Earth today that don't have states, right, in the same sense of a bureaucracy where people, their entire job is somebody's feeding them, housing them, right? They're getting paid, essentially, to organize things for the rest of us. What's the central function of the state? Let me tell a story to get you going here. Let's say you and I are herders in some tribal land in Afghanistan. And, our territories butt up against one another, and your dog kills my goat. What do I do? Anybody? What would you do? Well, that's one option, right? Maybe I go and talk to the guy, and he's really friendly, and everything's fine, right? Okay, maybe that happens. And I go, hey, man, your dog killed my goats. Can you give me one of your goats, right? And please keep your dog on a leash, right? Maybe I'm reasonable like that. But maybe he says, no, man, I don't know. I don't know how your dog died. It wasn't mine, right? What do? Maybe I go and kill his dog. Now, what happens if I kill his dog? Maybe he comes and kills my dog. Maybe he comes and kills a bunch of my goats. Maybe he kills me. What happens if he kills me? Well, maybe my family decides to go kill him. What happens if my family goes into this? This can go on for hundreds of years. And in fact, these kind of blood feuds actually are typical of these tribal civilizations. You'll have feuds between tribes that last for centuries, multiple generations. So I would submit to you that the primary role of having a king and having a bureaucracy, a state, is to mediate these disputes such that when the king rules, that's it. That's the end of the feud. There is no further argument. If the king says, all right, I decide that he didn't kill your dog, that's it. There's no more fighting about it anymore. And so this is the primary role, I think, of the state. This is why states evolve in almost every single hemisphere as a result of it. So as oppressive and tyrannical as these states tend towards, and of course they do tend towards oppression, they're essential for leading to a less chaotic situation than we would find ourselves in otherwise. Anyways, we'll talk more about that later, because it's really important. You know, you have to think twice before you start thinking about getting rid of everything that we've built for ourselves here. All right, so what the heck do these words mean? Anybody? Astronomos. Astronomy. Anybody?
Astro means space.
Stars. It's close. Stars. What about nomos? No. Nomos is law. These are Greek roots, okay? So essentially, and what's a law about that? Well, we'll talk about that in a second. So they're essentially coming up with these rules which govern the behavior of the sky, right? And this, of course, even the fact that the Greeks named it law can point to the bureaucratic nature of the way that astronomy and, of course, science today is also conducted. It's very, very bureaucratic, right? If I want to do an experiment, I have to go and essentially ask my government for money to do that experiment. I have to tell them why it's important, who's going to care, what amazing technologies it's going to lead to, right? It's a very bureaucratic discipline. So we essentially, and your textbook will maybe stop there, that astronomy, we come up with laws for what happens in the sky. Well, that's all well and good, and I think that coming up with laws is extremely important. It's very useful technologically. We can send spacecraft out to study Mars and Jupiter. We can do incredible things with these laws, right? Because they tell us the predictable behavior of the motion of our bodies, of the motion of these bodies. If we throw a rocket into space, it's got a predictable motion that's in some sense governed by universal laws of gravitation and momentum and all of these things, right? Very useful. But there's more to the story than the laws, right? Because again, science isn't just this predictive ability. There's something more to it too. There's something more about understanding the cause of the effect. Why is it that gravity falls off with an inverse square of the distance? Well, this is a question not too many people are concerned with these days. And I think that's a bit unfortunate, so we'll play with that. All right, two of my favorite words. These are going to keep coming up over and over again. Cosmos and chaos. So what is cosmos? Anybody? It's order, yeah. And obviously chaos is whatever the opposite of order is, right? So what these laws do when we're doing astronomy is they order the sky into something manageable, right? And again, I'm going to just keep hammering this into you over and over again, that pretty much everything that you do all day long is a battle between these two forces, right? At every step, right now, some of you are writing things down in your notebook. You're trying to order what's happening right now into something that's manageable, because otherwise it's just chaos. There's too much happening, right? The fact that we're all sitting here in these rows pointed forwards with our attention on one thing is a very ordered production, right? You don't come into this room and wonder, like, you know, there's nobody just comes up here and sits on the stage, and everybody knows what to do because there's an order that's been established for the way that we behave. And that's really important. It takes a lot of anxiety out of being alive to put order into these various situations. And so this is essentially what astronomy started as. It started as an attempt to order the universe into something manageable, something predictable, regular, something that didn't cause that overwhelming anxiety that would just tear things apart. Cool. And of course, that story is always on the move. You know, it's really remarkable, by the way. It's really remarkable that when we come into this room right now, nobody is afraid that the neighbor next door is going to just stick a pencil in their neck, right? But that's not entirely obvious why it's the case, right? We've all learned to behave that way, and people have just, you don't think about it. You don't think about, well, you know, I shouldn't do this or whatever. You're mostly just operating because that order has been established before you got here, because that order was established tens of thousands of years ago. And that's all part of the story of astronomy. Now, modern astronomy, this is a slightly modified version of the definition given by your textbook. So Astronomy, I'll tell you, the textbook definition was the study of objects that lie beyond our planet and the processes by which they interact with others. I've substituted the word body for object, and I think that's really, really important, actually. So, a body is a physical object. Now, you might ask yourself, why in the world would we have the adjective physical that goes in front of object? If, isn't an object, well, unfortunately, well, perhaps unfortunately, but objects in the modern sense can be quite abstract, right? If I have a data set, I can treat it as an object in mathematics. Now, this has led to, you might think that this is trivial and that I'm splitting hairs here. This is actually a really, really critical problem right now in science because we have this tendency to treat things that are not physical objects as if they are. Now, this is a philosophical fallacy called reification. This is mistaken concreteness. It's essentially mistaking a map for the territory. It's like if I had a map of, Crater Lake, and I said, okay, let's go to Crater Lake, and we just went and stood on the map, right? That would be a terrible travesty because we wouldn't get the experience of Crater Lake. This happens all the time in science, though, unfortunately, and particularly in physics, particularly astrophysics and astronomy. So listen, actually, here, case in point. I got this little magazine in my mailbox this morning over here at the university. I don't know what it is. I've never seen it before. But it just seems to be a general science magazine. What's happening? I flipped open immediately to this story. The story says, time is an object. Okay, well, time is not a body. It's not a material body, for sure. I don't think anybody would dispute that. But as long as we don't understand the difference between objects and ideas, we run into a lot of hurt. Now, you think this is not a problem, but look, every single word that comes out of your mouth represents one of those two things. It's either an idea or it's a body. That's it. All nouns, they're all ideas or bodies. They could be imaginary bodies, right? Like I could be talking about some character in a video game, some avatar. I could be talking about unicorns or something, right? They don't actually exist, but they still have those surface-bound volumes. They're still bodies, right? They're imaginary bodies. So what gives a body reality? What makes it real and worthy of consideration in our objective universe? It has a place also, right? It has a location. So we can't confuse ideas with bodies. If we do, we run into a lot of pain. And a lot of that pain is manifesting itself in the topics we're going to cover next semester with respect to cosmology. Yeah, we'll get into that more later. All right, so science, what's it trying to do? It's trying to make sense of phenomena. Science can get sidetracked by lots of things. It can get sidetracked by beauty. So what I have here is two different representations of the solar system. The solar system here on your right is the solar system that most people had adopted for the majority of human intellectual history, let's say since the time of the Greeks, okay? There's an argument to be made that this solar system is more beautiful than this solar system on the left. But almost no one would agree that this is the correct solar system at this point in time, okay? So why did we believe in the wrong model of the solar system for thousands of years?
Because humans were egocentric and thought they were the center of the universe.
That's a big part of it. That's a big part of it. So he said because we wanted to be at the center of the universe. That's a big part of it. But that's playing out today too, and we'll talk about that more later. There's something else that's really crazy about it though. This model, it's extremely predictive and extremely accurate. So it worked, right? This is why I'm absolutely going to be hammering into your heads this semester that the mathematics isn't enough to understand nature. It's a good starting place, right? Look, you can make these mathematical models. It'll give you something to look at, something to run your mind across so that you can see the patterns that are emerging. But it doesn't tell you the truth, right? It just tells you how things appear to be happening. And look, if you go outside, you're an ancient person, you know nothing about modern astronomy, and you look up at the sky, it's very, very true to you that there is a sphere passing over your head every night. That's absolutely true. You can make models, you can mathematize it, you can do all of this very high-tech quantitative reasoning on it, and you will come to the completely wrong conclusion, okay? So my point is, and we're going to talk about this story, and how it was overturned and all these things. Actually, your textbook absolutely loves this story. It treats it as like this, triumph of science that Galileo was able to dethrone this bad idea and so forth. But it's actually very, very difficult to dethrone an idea in science, particularly if it works. That's a nightmare, actually, if you think about it. Think about a lot of the ideas that we have today might work, but they might be completely wrong at the same time. That's crazy to think about. All right, so science can't just be predictive. It has to actually provide a cause for the explanation. There has to be a reason. And I think that the reason that this one triumphed up to this day, this one, the heliocentric model, is because they came up with the idea of gravity. And they were like, hey, the reason that the planets move the way they do is because they're all being pulled on by the sun, essentially. Now, the guy who came up with that, Newton, he didn't actually know why they were being pulled on, right? He said, they're doing it, they're being pulled on by the sun, but I'm not even going to mess with why that's happening. And most people since then have essentially followed suit. Don't really concern ourselves with material causes of that. And so there's a lot of work to be done in that department. Okay, so when we have these predictive models, the most intelligent thing that we could do as a species is to make a multiplicity of them, right? It would have been really wise if somebody would have not just concocted this model, but then kept going and tried to concoct this model and another model and laid them all out on the table and been like, which one of these makes the most sense? Which one has cause for this effect? But we don't do that, and we still don't tend to do that. In fact, we're really proud when we come up with any model that seems to work. We give people Nobel Prizes when their models work really well. This is maybe really dangerous, actually, because how do you ungive someone a Nobel Prize when it turns out that there's a better explanation for the thing that they got their prize for? A real mess, actually. So science is ultimately about possibilities for what could be causing the phenomenon, right? We start with these predictive models, these laws, and then we try to explain the cause of that effect. And this is something that you're not going to find in your textbook because it's really at the cutting edge of what's happening in the world of science right now. So here's my definition: mechanistic explanations for cause of an observable effect. Another one that's really confused, the hypothesis. And unfortunately, I love this textbook. I'm kicking the textbook a lot today. It's really rude of me. It's a fantastic textbook in that it updates in real time. So I'll actually be, I spend a lot of time reading the new literature that's coming out about astronomy and astrophysics. And sometimes I'll be going through the textbook and there'll be something that's out of date. They'll make some statement, particularly about one of the moons or planets, that's just wrong, right? We know something new about it now. And I'll think, textbook's failed again. And they'll update it while I'm reading the textbook, right? So it is a cool textbook. It's going to keep updating. But one thing that they've kind of confused, and I think a lot of scientists themselves have confused, and this is really cool if you can come to understand this, is that hypotheses and theories are not the same thing, okay? Theories are that explanation, right? They are that explanation that the sun is pulling on these planets and it causes them to move in this beautiful pattern that we describe using the laws of gravitation. That's the theory, right? And ultimately that theory is incomplete because we don't have a material explanation for that. People don't have a way of explaining why the atoms pull on one another. And we can talk about Einstein and all of this later. But needless to say, it's not a material explanation. So it's an incomplete theory, but it is a theory. A hypothesis is a little bit different. A hypothesis is something like, the theory is true if this is true. So this is René Descartes. He's a kind of pretty badass philosopher from France a long time ago. Came up with the Cartesian coordinates, a bunch of other things, studied the mind-body duality problem, which we can talk about at some point if we have time. And Descartes offered this definition for a hypothesis, which I think has not been beaten to this day. It's a supposition offered not necessarily as true, but if it was true, it would be sufficient to prove the theory. So, for instance, one hypothesis for why the planets go around the sun would be Einstein. The space itself is warped in some way. That's a hypothesis, okay? If it proved out to be true, then there you go. It proves the theory. Maybe the planets are tied to the sun somehow through some invisible fabric. That's a hypothesis. If it's true, it proves the theory. Okay. So hypotheses are that little unknown that you suppose could solve the theory. You can have a theory that is built on hypotheses in science. But what does it mean? Well, it means that the theory remains a theory. It's just a possibility of what could be happening. And you can put more and more faith in these hypotheses by picking at them and testing them in different ways. You can run experiments and so forth. Unfortunately, you can't really do these nice laboratory experiments on the stars that you can do, say, in biology, right? You can't grab a planet and stick it in a petri dish and poke at it and control it and have all of these nice conditions that you would expect for most experiments. So experimentation is a little bit out of the question in astronomy, which makes it even more exciting because we're dealing almost exclusively in the realm of hypotheses and theories. Now we can go to a planet, and we've been able to go to some planets. And so we've been able to actually check off some of these hypotheses and say, yeah, they are true, or no, they're not true. But in general, it's not so simple. So this is what's called hypothesis testing. It's how we can refine these observations and disprove potentially a hypothesis. We can rule it out. It's not always so simple, though, with something that's far away, especially when we're talking about something like another galaxy. There's no chance we're going to make it to another galaxy anytime soon. So how do you make up an understanding about it? Well, it has to be hypothetical in some sense. Your theories have to rest on hypothetical grounds. So the healthiest thing you can do is come up with lots of theories. And that's something that we're not doing a lot of right now, which is a little bit worrisome. Because that's the way that we come to know the world best, is by coming up with multiple theories. All right. All right, so, we'll run out of time here at some point, and I'll pick it up next week. But I do want to mention this while I'm on this rant about mathematics and theory and predictability and all of this. Look, you'll often hear this people say that mathematics is the language of the universe, or it's the language of science. Made a little movie, I put it in your Moodle. I want you guys to check it out. The topic of the movie is math actually a language or not? Yes.
I don't see the Moodle for the lecture. I only see the Moodle for the lab.
Really? Anybody else?
Yeah.
Okay. I'll launch it after class. Sorry about that. Yeah. Is math actually a language? Well, I mean, punchline is that it's not. It's actually quantitative adverbs. You can't actually string sentences together with quantitative adverbs. So any mathematics that you provide have to require some sort of additional language in order to qualify them. You have to tell me what the variables mean. You have to tell me what your equation actually means with respect to the natural universe. Okay? And so we can run into a lot of headaches when we start thinking that mathematics, look, I love mathematics. It's extraordinarily useful for technology, but it can get us in a real headlock when it comes to understanding the natural universe, because we can understand the mathematics very well, and we can be completely clueless about what's happening in the natural world. That's really something to impress upon you guys as you go out into the world, because I don't think most of you aren't going to become scientists. That's totally fine. But you're going to encounter people who are going to try to bludgeon you with science as you go out into the world. And they're going to try to whip you around with it. It's very important that you understand that mathematics is not science. That mathematics, you can prove things. In science, the best thing you can do is rule out an explanation. You never prove anything in science. Proof is for math. Proof is a logical argument. It's an if-then situation. If this, then that. So all of the proofs that you hear about rest on assumptions in science. They all rest on some sort of conjecture that says these are the qualities that we're expecting to be the case. When we talked about radioactive radiometric dating at the beginning, the assumption is that this rock was melted when it was formed for the first time. Okay, it's a huge assumption actually, and you're never going to hear about it from anybody. And it might be reasonable. That's the thing. It might be a great assumption. It might be true. It might not be true though. So check out that video. I think you'll enjoy it. I think we've covered all this. Look, when we say nature is a real dirty word in science. It's very difficult to get your hands on. I think generally what we mean when we say nature in this class is things that aren't made by humans. I think it's that simple. Now, this is obviously a kind of preposterous definition because, of course, humans are natural. It's not like we're some sort of thing outside of the universe, right? We're part of the party as well. So humans are perfectly natural. But just to keep things clear, when we talk about the laws of nature and so forth, we're talking about things beyond the praxis of human interaction, right? So don't get confused about that. This is something you might need for, but you can read about this in your textbook to some extent. Have you guys encountered scientific notation before? A little bit? It's pretty easy to get a grip on. So essentially, a lot of the distances that we're going to be dealing with, how far away some of these bodies are, they're really too big to put a number on very easily, right? They're going to be trillions, if not more, like thousands and billions of trillions of miles away from us sometimes. So instead of trying to write these huge numbers out, we essentially do this thing called scientific notation. All it means is when we have a really big number, we're going to approximate the number of zeros next to it by essentially counting up all those zeros and writing times 10 to the power of whatever, that number of zeros. That's it. If you want to do something really small, which we won't be doing too much of in this course, you do the opposite. You're going to move that decimal place over the exact number of times, and you'll say 10 times 10 to the minus whatever power it is that you've moved your decimal place to the left. Okay, you can read more about that in your textbook if it doesn't make sense. We're going to be dealing with SI units. This is System International. This is the meter and the kilometer. If you ever get lost, you can essentially get between miles and kilometers by multiplying by about 0.6. That's a useful frame of reference. It's important to standardize these, otherwise different countries will be talking in different ways and it just gets too chaotic. All right, and then let's just end here. I want to make one last point about all of this. We can't run a measuring tape out to most of these planets. We can't actually measure the distance to the stars, right? All we have is light. And so one thing this is both a blessing and a curse, is that time and distance are inseparable when it comes to looking at the sky, all right? This is assuming that the speed of light, how long it takes for that light to reach you, is constant. And it appears to be constant by all available measurements in a vacuum, like say the vacuum of space. And space isn't a vacuum, so this gets complicated, but it's very close to a vacuum. So when we talk about distances, we're actually going to be talking about things like light years, which gets very bizarre because now time is turning into a distance. This is something we're going to have to live with and mediate with because, again, we don't have the luxury of a nice laboratory where we can poke at stars and poke at suns. We're making all of our conclusions based off of light, which is coming down to us. That's it. Everything is indirect in astronomy, which makes it a real puzzle going forward. So next time, we will get a bit more into the nitty-gritties of the way that the sky is chopped up in modern astronomy, and we're going to keep talking about why it's important, how other people saw it, and what it meant to them. And anyways, I hope you will take the course. Please drop it if it doesn't sound fun, and I will see you guys on Tuesday. Have a wonderful weekend.
Thank you.